At some point, some tensors will appear, but not immediately. So if that's really the only reason you hear, then bear with me, they will come up. But I'd like to kind of just set the stage first. So I should say,
yeah, can you just
okay, try. Okay, yeah, I'll try.
There's also seats up here.
I'll do my best. If the font size decreases, just please yell, okay? Then I'll start to write bigger again. Yeah. So this is joint work with Harry Buhrman, Davi, Castro-Silva, and Niels Neumann. And the motivating problem for this whole talk has to do with error correcting codes. So very briefly introduce those. Is that big enough?
it's fine, thank you.
All right. Try not to. So, okay. So for the purpose of this talk, an error correcting code is just a map E from k-dimensional vectors over a finite field to n-dimensional vectors over a finite field. So here, for the purpose of this talk, F is a finite prime field whose characteristic is constant. Okay, so this will be relevant in a bit. Okay, so the basic property of error correcting codes is that the images, so say this is a point E of x, are well separated in Hamming distance. So here there's two points in the image of this map, and what you want is that any 2 points in this image differ in many coordinates, and the basic purpose of this is to protect information from corruption. So if this code word, which encodes a message x, gets corrupted in a few coordinates, so you end up with something that's slightly removed in Hamming distance from the original, then if it's not too corrupted, there will only be a unique code word of closest distance to this corrupted version, and so you can then uniquely retrieve the encoded message. Okay, so in a nutshell, that's what error correcting codes are about. And I mentioned corruptions. So there's a very basic probabilistic model that tells you how error correcting codes may get corrupted, and that's the symmetric channel, which models noise. And so for the purpose of this talk, the noise is modeled by a random vector, z, that has, n independent coordinates. So each zi is independent and identically distributed as the others. And the distribution over these coordinates is such that zi is 0 with some probability rho, and I'll refer to this rho as the bias of the distribution. And with probability 1 minus rho, this coordinate is uniformly distributed over the elements in the field. Uniform with probability 1 minus rho. Okay, so suppose I might get questions about this later, so let me just write it down here. Here, F is a prime field characteristic P. This lowercase p will pop up here and there. I'm afraid I don't have enough board to leave this on, so yell if you don't recall what lowercase p is. For our purposes, p is just a constant. But what I'll say holds more generally. Okay, and so the basic problem in this setup, the goal is.
Sorry, Ci is over Fp, right? Is that right?
Zi is over Fp, yeah. So it's a uniformly distributed element over the field. And so if rho is 0, then it's unbiased and Z is completely uniformly distributed. All right, and if rho is equal to 1, then Z is just nothing and there's no corruption. So it's the bias. Okay. So the goal in this setup is to try and decode, sorry, that's too small. Decode an encoded message X from a randomly corrupted version of its corresponding error correcting code. Okay, so E of X is the encoding of X via the error correcting code, and some of its coordinates have been corrupted by adding to it this random vector Z. Oh, maybe I'll use this word still. All right, so this project was about certain ways to try and achieve this goal. And the mathematical version of the method that we studied to try and decode had to do with a thing called polynomial maps. So a polynomial map, phi, is a mapping from f to the n to f to the k. So e goes from k to n, and phi goes from n to k. So it's supposed to somehow invert the error correcting code, even if there's corruptions. And this thing is called a polynomial map if its coordinates are given by polynomials. Fk, where each fi is an n-varied polynomial over the field xn.
Do you care about the efficiency of decoding, or do you just ask if it's possible? What's the
Efficiency will come up in the degree. So maybe I'll answer your question in a second. Okay, so so ask again if you're still not satisfied in a few minutes. And then the degree of such a polynomial map is defined as the largest degree among the polynomials that define it. So the maximum degree among the fi. And then right, so I'll say phi has degree at most d if all of its coordinate polynomials have degree at most d. And it'll be convenient to introduce a bit of shorthand. So I'll denote by all at most d, f to the n, f to the k, the space of polynomial maps from f to the n to f to the k, whose defining coordinates all have degree at most d. Okay, so there's a question about efficiency of decoding. So what these polynomial maps allow you to do is represent in a mathematical way a very basic class of circuits that was of interest in this project. So this class of circuits, to give it away immediately, is NC0 with parities. In the case the field only has two elements, and if the field is larger, then this parity is replaced just with a sum mod p. So very briefly, what is such a circuit? Such a circuit can be modeled as graph that looks like this. It has n input leaves. So what goes in on the bottom is a vector from f to the n. Then a bunch of gates, each so arbitrary, but each depending on at most two coordinates at a time. Okay, and maybe some more layers, and then on the top, k output leaves that are supposed to spit out an element in f to the k. So the number of layers here is constant. Okay, that's what this 0 stands for. These gates are arbitrary, have fan in 2, except for one privileged gate, and that's the parity gate. So there's one gate that you're allowed to use that's allowed to depend on all possible leaves, but is allowed to compute only the sum mod p, or in the case of up2, the parity. Okay, good. And so there's a translation between the types of functions such a circuit can compute from f to the n to f to the k and polynomial maps of constant degree. Okay, for any polynomial map, you can construct a circuit that computes it and vice versa. Okay, but the degree doesn't, okay, so maybe to preempt a question, the degree of the polynomial map grows exponentially with the depth of the circuit because degree is multiplicative under composition, but we assume that the depth is just constant. Okay, so we were interested in how well can NC0 with parity circuit perform this task, decode a randomly corrupted error correcting code. That was a main question. So we suspected that these types of circuits are very bad at this for any error correcting code. And this is good because this was a preliminary result of Harry and Niels. There's an analogous quantum circuit, a QNC0 circuit, that is quite good at performing this task for a specific type of code called the Hadamard code. Okay, so this would showing that these circuits are bad at performing this task, or equivalently that polynomial maps are bad at decoding, in a sense gives you a separation or a key difference between a basic class of quantum circuits and their classical analogs. That was the gist of the project. Okay, so perhaps to give a little bit of more context, of interest for us was the setting in which the bias rho is a constant, strictly between 0 and 1. There's previous results by Emanuel Viola that say that even a stronger class of circuits than this one, where the Fanning gates is unbounded, AC0 with parities, is bad at performing this task when this bias goes to 0 with the length of the code, the number of encoded message bits. Okay, but for that, this bias needs to go to 0 sufficiently quickly, and we were interested in the constant bias regime. Let me just get right to the main result. So that the main result I want to talk about today is what I alluded to, which is that polynomial maps or NC0 circuits with parities are bad at this task of decoding randomly corrupted error correcting codes.
Sure.
Yes.
You have to repeat it again. I think I missed when you said it. So what is this with parity? So is there a separate gate?
Yeah.
Parity?
Yeah. So all the gates have Fanning at most 2, but do something arbitrary. But there's one privileged gate you're allowed to use whenever you like. And that's the parity gate. So so I didn't
All of them
arbitrarily many. Without loss of generality, you can move them to the last layer if you like, since the depth has to be constant.
Yes.
But yeah, so there's the gate set you're allowed to use is arbitrary Fanning 2 and the parity gate, and you're allowed to use as many or few as you like.
And there's no fan outs.
There's no fan out.
So I can't duplicate. Can I duplicate with the input?
You can, yes. Okay, so maybe my drawing is bad. So these two guys are allowed to use. This is what you're interested in, right? Yeah. So you can use the same leaves as many times as you like.
Okay.
Yeah. Fan out is arbitrary. The main result that I kind of want to discuss in the language of polynomial maps says the following: that there is a K0 which depend on the degree of a polynomial map, an epsilon of your choice, and the noise parameter rho, such that if K, the length of the messages you're trying to encode, is sufficiently big, so at least K, and phi is a polynomial map of degree at most D, from F to the K to F to the N, then the probability taken over a uniformly random message F to the K and a noise string Z distributed like this, which I'll denote by script N sub rho, that this polynomial map phi, when given a corrupted version of the code word corresponding to the message X, returns X, is at most this epsilon of your choice. Okay. So this result shows that NC0 with parity circuits are terrible at decoding error correcting code, no matter what your error correcting code is. Okay, so I've made no assumption. Oh, sorry. So E is something like, I should have defined it in the statement of the theorem. Maybe I'll continue. Or any E from to the K to F to the N. Okay, so no matter what your error correcting code does, whether it's good or bad, you're not going to be able to decode it well under random noise with an NC0 with parity circuit. That's the gist of this theorem. Yeah.
So I think the notation is the other way around, but it came so with the poly.
Yes. Thanks. Yes.
When is the epsilon chosen?
Up here. So you choose epsilon. So this is how bad you want the circuit to be at decoding.
Epsilon rho.
Yeah. So K0 depends on 3 parameters: the degree of your polynomial map,
Yeah.
an epsilon that you choose in advance, and the noise parameter rho. Once you've chosen these things, this will hold. So epsilon is an upper bound on the probability with which your polynomial map correctly decodes your error correcting code.
When is the N chosen?
Yeah, so N is, it doesn't appear here. So the statement gets trivial when n is much smaller than k. In that case, you're compressing messages, and in that case, I suppose there's a tailored simple proof for this result. But what's important here mostly is the length of the messages. So this holds for any n.
That could be huge.
And yeah, n could be huge in terms of k.
Yes.
Yeah, but the point here is that k has to be sufficiently large for this decoding to be difficult. So that's the typical case in error correcting code. Like the length of the messages is something that grows asymptotically. There was another question.
Oh, yeah, I think that's it.
Short answer. Okay. Okay. All right. So stop me if there's more questions, of course. Good. So I mentioned Viola already. So this is his territory, and we did our best to read his literature to find out if there's something was known. And the thing I already mentioned about AC0 is the best we could do, but it didn't capture this setting. And so in a blissful state of ignorance, we found a proof for this result. And then I talked about this a few weeks ago, and I was kindly contacted by Emmanuel last week, asking if I could perhaps have a look at claim 31 of a paper that he attached. And what claim 31 contained was a proof of this statement for particular types of error correcting codes that are k-wise independent after restrictions. Okay. I'm not going to go into the details of what that means. What it does mean is that his result captures the Hadamard code that was of interest in the separation between classical and quantum circuits. So had we known this a year ago, the buck would have stopped there, and I wouldn't have given this talk here. But so we have a different proof that philosophically is somewhat complementary to what his approach suggests. So he looks at properties of the error correcting codes and works from there. What we did instead is ignore what the error correcting code looks like and instead look at what polynomial maps phi could have via properties. And this turned out to result in some questions, for example, about tensors and ranks for tensors. And that's why I'm talking about this now. I should keep an eye on the time. Good. So there was some results from a higher order Fourier analysis that I hoped would be applicable to prove this result. And those results, they talk about the unbiased setting. And I quickly want to mention them because the notion of rank pops up there. And it turned out to be relevant in the proof in the end, but not in the way we expected. So in the unbiased setting, there's this definition of D rank for polynomials introduced by Green and Tao about 15 years ago. So for say a map from f to the n to f, they defined the D rank, ranks of D of f to be the smallest positive integer r, so that you can decompose f, a sum function gamma of polynomials q1 up to qr, whose degree is at most d. Ui is, okay, I guess I can use my notation, all at most b from f to the n to f. Okay. So that's the D rank. And for this D rank, they showed the following result that I hope would be useful. Green tau. There's a comma.
Gamma.
Gamma is some arbitrary map. Okay. Yeah.
Arbitrary map.
It's some arbitrary map. It doesn't have to be polynomial. From f to the n, sorry. Yeah, from f to the r to f. Yeah. Okay. So gamma just depends on our things. So Green and Tau proved kind of in the high characteristic case, so if the degree is strictly less than the size of your field, that if okay, I'm gonna let's see. Right. So if phi is a polynomial map, degree at most d, from f to the n to f to the k, that satisfies a certain regularity condition, which is to say that for every non-zero vector, the polynomial you get by summing the defining polynomials of your polynomial map with the coefficients from V, which is to say the inner product between V and phi, say the D minus 1 rank is at least R. This is some kind of regularity condition on the polynomial map. Every possible linear combination of the defining polynomials of phi has high D minus 1 rank. Then you get something that's referred to as equidistribution. And the probability over a uniformly distributed, let's call it a noise vector, that phi of z plus any arbitrary y, which I suppose you could think of as an e of x, and a code word, is equal to some vector w, which also of your choice, is at most something small, epsilon, that depends on the characteristic of your field, the lower bound on the rank you have, and the degree of the polynomial. Okay, so this holds for every y and w. So this shows that if your polynomial map phi is quasi-random in some sense, it satisfies this regularity or rank condition, which is what you would expect if your phi is randomly sampled, then it satisfies something that's referred to as an equidistribution result. Okay, but this applies to regular phi and uniform z. So it doesn't match up perfectly with what we were after. For one, we make no assumptions on the properties of our map phi. So it doesn't necessarily have to be regular in this sense, but they have some very nice techniques to force an arbitrary map to be regular. So it turns out that you can restrict your map phi to a partition formed by algebraic sets, so that restricted to each of these sets, phi looks regular in this sense. Okay. Yeah.
I'm a little bit lost.
Okay.
Sorry. F is equal to, I'm still looking at the definition. I didn't manage to get it.
This one. Okay.
Yes. So F is equal to what? Gamma.
So you want to express f as some function of R polynomials whose degree is at most d.
Okay. So where is the okay? It's a some function. Okay. Of this.
Yeah. Okay, so there was some nice techniques, but it wasn't really clear how to apply them. So there was some issues with this thing, but it seemed like there was some literature out there. I alluded to one issue, like we don't have regularity for a map phi, and the second issue is that this deals with uniformly distributed z's, but we had biased noise vectors. So it's not immediately clear how to translate their result to supply a proof for this theorem.
The regularity, what did you write? The rank, D minus 1 rank of what? The inner product.
Yeah, so phi can be thought of as a vector of k polynomials. And now here we're summing each of these polynomials with the coefficients from a non-zero vector v, so that results in a polynomial.
That's a length k vector.
V is a length k vector, yeah. Sorry. I had complaints about my k before. Yeah. So all non-zero linear combinations of the defining polynomials of phi have to have large rank. This is something you would expect when phi is randomly chosen. Okay.
Saying what this rank is called.
The D rank, as far as I know, I don't know if there's a good word for it. Yeah. Okay, so the first issue is that our phi is not regular, and there's not a clear way how to force it to be regular. But then there's this paradigm from additive combinatorics or higher order 4 analysis that instead considers a case analysis based on whether your whatever object looks random or it doesn't. So the structure versus randomness paradigm. And this kind of case analysis turned out to be useful to prove our result. And to see an example where showing that this is the case, it's instructive to already consider the case where the map phi we're given is affine linear. And this is where you see rank functions appear. So suppose that our map phi is given by some k by n unitary matrix U plus possibly an affine shift V. And suppose that the goal is to prove for this map this result. Okay. So we're sampling over uniform encoded message X and a noisy Z here. And you can do a case analysis based on the rank of this matrix U. So first case, kind of the generic case, if U has large rank, or sorry, okay, so here in my notes I did the low rank first. So suppose that U has low rank, so at most k over 2. So think of U as k by n matrix. Then the probability over a uniformly selected message after the k, ignoring for the moment the vector v or fixing it, that phi of x plus z is equal to x. So this event happens only if x lies in a coset of the image of phi, okay? Particularly the coset of the image of u shifted by v. So this happens only if x lies in the image of u plus the shift v. But since u has rank at most k over 2, this happens with exponentially small probability. So you can bound this from above, just from the fact that u has tiny rank, that this is at most lowercase p, that's a characteristic, to the power minus k over 2. So you have exponentially fast decay of success decoding in this setting. The second case, that's kind of the generic or high rank setting.
So is the rank of U, the subamount of rank of U, is that an assumption or?
That's an assumption. So this is a case analysis, supposed to be a simple example of where this structure versus randomness strategy works out.
Is there examples of your theorem or of the?
Of this theorem, yeah, of this one. So the goal is to prove this. Yeah, exactly. So this is a simple case. And the outline of this proof turns out to work well for higher degrees as well. But for that, you need to introduce new notions of rank. And you need to study properties of that notions of rank that in turn lead to questions about tensor rank, rank for polynomials and polynomial maps.
Sorry.
I'm sorry?
But in this theorem on the left side of the board,
This one?
the phi has like an upper bound on its complexity, right?
The degree is an upper bound on.
Whereas in the green towel thing, it has a lower bound. So, like
Let's
the
see.
rank, the d-1 rank.
So there's no rank in this statement, right?
Yeah.
So there's a degree upper bound, and here there's also an assumption on the degree of phi. So that's something fixed, constant degree. Yeah.
But so shouldn't it like get easier to break it, to decode when the phi is more complicated?
Yeah, so this is, by more complicated, I suppose you mean something like this. Yes, that's what you'd expect. Yeah.
But it's like the opposite statement, or am I missing?
Oh, so this is saying that,
like if the phi is kind of complicated,
yeah,
meaning the rank is bigger than r,
yeah,
then
decoding is hard.
Decoding is hard.
Yes.
But wouldn't we have assumed, or would that have assumed that if my phi can be more complicated, then that gets easier? I mean,
well, yeah. So that's in a sense that's the case.
That's one way around the equality.
Yeah, I suppose that's true, but this doesn't capture the non-complicated part yet. So that's in the linear case, that's captured here. So the non-complicated part is the low rank setting. And in this case, you see that your simple object does very poorly. Okay. The problem is that if your object is complicated, then the noise that you're adding to the vector that's going to screw you over because the complicated object is going to translate this noise into randomness in its output.
Okay.
Maybe that's some intuition. Okay, so to continue the case analysis, if the rank of U is big, which is more like the quasi-random case, at least n over 2, you can do the following. So now suppose we consider only the noise and the event that we wish to bound. And for this, what's useful is to think about what this noise vector looks like. Okay, so what I said is that its coordinates are independently and uniformly independently distributed, and with probability rho they're 0, and probability 1 minus rho they're uniform. Okay, so you can think about sampling such a z in 2 steps. First, you sample the coordinates on which it's 0, and then among the coordinates in the complement, you take z to be uniform. Okay, so instead, I'll write this probability as well. Okay, so let's and rho. So this is equal to probability now over a random subset I from the n coordinates that independently include each with probability 1 minus rho. So I is going to be the subset on which our vector v is uniformly distributed. Everything outside of this is going to be 0. Y is uniform on this subset I. Okay. You can rewrite this a little bit, and what you wish to bound in the end is the probability that the submatrix U, where you restrict its columns to the subset I times Y, is equal to some fixed vector V. So here you look at the restriction of U to the columns that are indexed by this randomly chosen set I. Now, if U has rank at least k over 2, and rho is constant, then with good probability, this random set is going to contain a significant proportion of linearly independent columns. Okay, so suppose you have a set of at least k over 2 linearly independent columns, and each is selected by I with probability 1 minus rho. So by the turn-off bound, within I, you're going to see a fairly large fraction of linearly independent columns. Y is uniformly distributed, so this means that this random element here in Fk is going to be approximately uniform. It's going to be well equidistributed. W is fixed, so when you do the calculation, you get that this is bounded from above by, again, something that decays exponentially fast in K, with an exponent that might depend on the noise parameter rho as well. Oops, there's a minus there. So this is a case analysis based on rank that proves this result when D is equal to 1. This case analysis separates 2 ideas. Either U is simple, has low rank. In that case, the uniform distribution over X causes it to perform poorly, or U has high rank, and then the noisy distribution over Z, and the fact that the randomly restricted matrix will have high rank when it has high rank itself, causes this distribution over Z to perform poorly. Yeah.
There's no W in the first line.
No. So I mean, W is something you get by rewriting this. It's some fixed vector that incorporates the vector V there, and this E of X and this X. Okay, so it's a dumpling of those things. It's fixed.
The first argument for K for the rank greater than K over 2.
What goes wrong with the first? Well, so let's see. What are you saying? If the rank is really big, let's see. I don't know. So I don't know. So it's just this step, right? So this image, let's see, could be right. So this image will be huge then. And so, like, if then the probability that if you just look at this probability, that might be quite big actually. If this is a huge affine subspace, and the probability that the uniform X lies in there could be constant, but the goal is to prove something very small. so okay. But this is just an example to show how in the end the proof of that statement turned out to work. So the proof of the general statement that we came up with works the same, but now for a new notion of rank for polynomial maps. So I'm slowly progressing towards a connection with tensor ranks. So we considered a similar case analysis as we did for the matrix case based on a rank function for polynomial maps that we called analytic rank. So the definition is as follows: for polynomial map phi, polynomial of degree at most d from f to the n to f to the k, its analytic d rank is defined as minus the logarithm base lowercase p. So p was the size of the field we're working over, of the maximum over similar polynomial maps, but of degree at most d minus 1. So I'll just write it like this: degree of phi strictly less than d, of the probability over a uniform element to the n, that phi is equal to psi. So what's in here is the maximum over polynomial maps of degree strictly smaller than d of the proportion of points on which our polynomial map phi agrees with phi. To give you slightly more intuition, let's look at the affine linear case again, and there you'll see that matrix rank pops up again. So phi is as I had before.
It's called the uniform distribution.
This is the uniform distribution. That's right. Yeah. So in our case, z will not be uniform, but you can interpret. So this is an important point. You can interpret what you do here as looking at a uniform distribution over a random restriction. Okay. You can interpret z as first choosing the restriction and then a uniform distribution within that restriction. Okay. So phi is affine linear. Then for any w of your choice, the probability that phi of y is equal to w when y is uniformly distributed can be worked out to the following. It's either minus p to the minus the rank of your matrix if w minus v lies in the image of u. Okay, so w is some fixed vector, v is the affine shift, I suppose, and it's 0 otherwise. Okay, so this phenomenon motivates choosing a maximum over maps 5 degrees strictly less than the map that you're starting with. Okay, so here phi has degree 1, w has degree 0. And so by choosing w judiciously, you can make the matrix rank appear. So for G1, you get the matrix rank. For higher degrees, you might get something else. Okay, so this is the notion of rank we use for our case analysis in the end. Okay, so now finally I come to tensors. So there's a question about this analytic rank. We called it analytic rank for the moment just for aesthetic purposes, because it reminds one of a notion of analytic rank for tensors. Good, so I'm glad Harm already introduced a few things. So one can think of a tensor as a multilinear map on the default Cartesian product of f to the n. And then the analytic rank, which was introduced by Gowers and Wolf some time ago, concerns a parameter called the bias. So the bias of t is equal to a uniform distribution over d uniform independent random vectors y of omega. This is a pth root of unity, this multilinear map T evaluated at these d vectors. Okay, so here omega is e to the 2 pi I over lowercase p. So this is the bias.
Shouldn't it be like a log? Isn't it a log rank that you define? Or is it really a rank?
It's a rank. So if you look at this case, I've just I've just inserted here what I have here. So if you take the minus the logarithm base p, you get the rank of the matrix. So to find the analytic rank is minus the log base p of the largest probability you can get here. Okay, yeah. So here's one expression for the bias. There's another expression that Harm wrote down that allows you to rewrite this as follows. This is also equal to the probability that a degree d polynomial map naturally defined by t is equal to 0. So this is equal to the probability when you take d minus 1 independent uniformly distributed random vectors minus 1 to the n that t now only evaluated at these d minus 1 coordinates and with its last coordinate set free. So now you have the degree d minus 1 multilinear map from f to the n Cartesian product d minus 1 times to f to the n is equal to the all zeros vector. So that looks a little bit more like what I have in the expression for the analytic d rank. Then the analytic rank of t is defined minus the logarithm base p of the bias of this tensor t. Okay. Now the question is this analytic d rank, analytic rank of the tensor equal to the analytic d rank of the multilinear form of the polynomial map naturally associated with this tensor t like this? So the question is this analytic rank of the tensor equal to the analytic, sorry, I should say d minus 1 rank. It should correspond to the degree of the object. Let's call it phi sub t. Okay, where by phi sub t I mean this object. So this is a polynomial map, degree d minus 1 that spits out n-dimensional vectors. So this I don't know. Okay.
What's the easy direction? So there's an inequality, right?
There's an inequality, yeah. So here you're allowed to take the maximum over all psi's. And the question is if for these particular types of polynomial maps, this maximum is attained when the psi is equal to 0. Okay. Yeah, and that I don't know in this setting. I should keep an eye on the time, I suppose. Okay, so like I said, to prove this result, we do a case analysis, and that's somewhat analogous to what I did for the matrix case. You consider something of high rank or something of low rank, and the rank notion we use is this analytic rank for polynomial maps. So I want to switch the order around that I had planned because I'm going somewhat slower. I want to say something about what happens in the second setting for polynomial maps. If the analytic D rank of a map happens to be large, because that leads to some questions about tensors that are quite natural, but whose answers are not understood as far as I know. Board doesn't seem to be behaving well.
Can you say what phi sub t is?
Yeah, sorry, I was quick about this. So Harm suggested it in his talk. So T is a multilinear map. Okay, so you can also think of it as a degree D polynomial. Okay, and now what I'm doing is I'm viewing it also as a map of the D minus one fold Cartesian product. So D minus one into f to the n. So still a multilinear map, but this is what you get when you leave its last coordinate untouched. Okay, yeah. So and that's what I meant. Well, that's what I mean by phi sub t. So to degree d minus one polynomial map from f to the n to f to the n, or the Cartesian d minus one fold Cartesian product of f to the n to f to the n. So this is case analysis, usually called the structured case versus the quasi-random case. The quasi-random case considers the setting in which the rank is large, which should be thought of as your map behaving somewhat randomly in some sense. Okay. Suppose that the analytic D rank of our polynomial map phi is large. Some parameter r that you have to choose judiciously in the end to make the proof work. Let's just take some arbitrary r at the moment. So in this case, we want to prove this this statement here. And what we'll do actually is fix x, and just show that for any fixed x, when you sample over the z, this probability is going to be large. Okay, in this setting, when the analytic D rank is big. And so the main lemma that we use for this, we had to prove, is what we call a random restriction lemma. Random restriction. So yeah, to be precise, it says the following. There is some r, which depends on d, some sampling probability sigma, and a parameter epsilon of your choice, and a kappa, which depends on d, and the sampling probability, such that if phi is a polynomial map of degree at most d, from f to the n to f to the k, with analytic D rank at least capital R, then a random restriction of phi to a subset of coordinates that appear independently with probability rho will also have fairly large rank. So more precisely, and the probability over a Bernoulli random set of the coordinates on which phi is defined, and where each coordinate is present independently of the others with probability sigma, the analytic D rank of the restriction of phi to this coordinate set, which is what you get by evaluating phi only to those vectors that are 0 outside of I, so it's kind of the restriction. The probability that the analytic D rank of this restriction is at least kappa times the analytic D rank of phi is at least 1 minus epsilon. So in short, random restriction lemma says that if the analytic D rank is large, then a random restriction of it will, with high probability, also have large analytic D rank. So this is the main tool in proving this statement. And the reason why you can use it to prove this statement is because you can interpret this distribution over the noisy vector z as first selecting a set of coordinates on which z is going to be non-zero, and then taking the uniform distribution over those non-zero coordinates. And the analytic D rank over here was indeed defined based on a uniform distribution. Okay, but now we're going to apply this to a restricted version of our polynomial map phi. So that's why you can use it. So there's a kind of a natural way in which you might hope to prove this random restriction lemma, inspired by the way you might prove it for matrices. Suppose that you have a matrix whose rank, say, is at least R. And what you might want to show is that a random restriction of this matrix will still have a big rank. But that's the case, right? So suppose that this is a set of R linearly independent rows. And if you pick each of the rows independently with some positive probability, sigma, then by the turn-off bound, so say, I don't know, this is your random set over here, that's I. By the turn-off bound, with good probability, you're going to capture a good fraction of these R linearly independent rows. Okay, you can play this game again now. So this subset of rows that's included in the set I that you sampled will have a set of linearly independent columns here. So now if you pick an independent random set J from the set of columns from your matrix, with good probability by the turn-off bound, you're going to capture a good fraction of those linearly independent rows that are captured in I. And so in the end, you're going to sample a random I by J submatrix with large rank. Okay, so in a sense, you can prove this type of result for matrices using the fact that there's a high rank core present somewhere in your matrix, and the fact that we're sampling independent, the rows and columns or the coordinates independently. But that's not how we could prove this, because there's no such result known for polynomial maps. So what we don't know is whether if your map phi is high rank, then there's a coordinate restriction that's relatively small, whose size is roughly the same as the rank, such that this restriction also has high rank. That's not the way we prove it. Instead, we use ideas from analysis of Boolean functions. So definitely don't have time to go into that. I want to say a few more general things and ask a question. So the general thing I want to say is that we can prove a result like this, not just for polynomial rank, but for fairly natural functions that resemble properties you would expect from a rank function. So for both polynomial maps and for tensors, we can prove a result like this for things that we call natural rank functions. And we say that a rank function on a set of polynomials, polynomial maps, or tensors is natural if it satisfies a number of criteria. So it has to be non-negative, it has to be monotone under restrictions, by which I mean coordinate restrictions. It has to be subadditive, so the rank of a sum is at most the sum of the ranks, and it has to satisfy a certain Lipschitz condition.
Some being important.
Sorry?
Some is supported by some.
Some, no, I mean, if your rank function of the sum of two objects, so polynomial maps, polynomials, or tensors, is at most the sum of the ranks. That's what I mean by a subadditive. And it has to satisfy a certain Lipschitz condition, which, roughly speaking, says that the rank doesn't decrease too much when you restrict. So monotonicity says that your rank can only decrease if you restrict it. Lipschitz condition says that it can't decrease by too much. Okay, so and these are properties that are satisfied by many of the well-known rank functions we see. So slice rank for tensor satisfies this. Partition rank, geometric rank satisfies it. Tensor rank doesn't. So tensor rank very badly fails the Lipschitz condition.
What is the Lipschitz condition? Can you explain it?
Sure. What's that?
Can you write on the technical definition of this?
So it says that your rank function, so the rank of the restriction of I restricted to the union of two sets is at most the rank of the restriction to the first set plus the size of the set J. So for tensors, for example, this is equivalent to saying that the rank drops by at most one if you take off a slice.
For tensor rank, it's false.
For tensor rank, this is false, yeah. And you can kind of artificially try and normalize things, but you're not allowed to do that because the normalization is not. It's because
it can be very high.
It can be very high. It can be as large as n squared. So that's a problem with tensor rank. Yeah, that's right.
It's quite general, like the zero function is also allowed in the net.
I suppose, yeah.
You don't normalize. Yeah, you don't. Yeah.
Yeah, I suppose that's right. Yeah.
Okay.
Yeah.
Maybe not in there.
Yeah, I was wondering about that. So I didn't look at the subrank. For polynomials, in the analytic rank for tensors satisfies this. This analytic rank for polynomial maps satisfies these properties. The so-called Schmidt rank for polynomials satisfies this. I'm not going to write it down right now.
It's only stuff that is subrank, like stuff that lies at the lower end because the maximum is pure local dimension, right?
Yes.
Otherwise,
because of the Lipschitz condition. Yes.
Why don't you use like a constant?
Yeah. Okay. Sure. You could. I suppose.
Like say rank plus a constant times J.
But it has to be an absolute constant.
Sure.
It's not allowed to depend on the dimensions. Yeah. That works. That's fine too. So then this constant pops up in the random restriction theorem. So my time is up. I just wanted to ask the question that I guess Thomas Karam will also touch upon later this week. What's the the best core you can find for any of these rank functions. So suppose that you have a rank function on tensors, polynomials, polynomial maps that have rank at least R. What can you say about a restriction whose rank will also be big? And can you prove that there is such a restriction whose size is linear in R, such that the rank of this restriction is also at least linear in R? So we don't know that for any of these functions. And Thomas has results going in this direction, but they're quantitatively not strong enough to prove what we want. So I'll leave it here. Thanks.
So in your book, does the property of the code come up?
No. So that's the thing. We instead take the code to be arbitrary and do a case analysis based on the polynomial map or the circuit, if you will. So Viola, like I said, has results that pertain to specific types of codes. And so if the code is k-wise independent for sufficiently large k, then our result holds. And I'm wondering if you can interpret that also as the onset to structure versus randomness type proof, but where you take the code to be the object that's being analyzed. So k-wise independence seems to be like a quasi-random type property. So if the code doesn't have this property, maybe the code is very bad. It's structured in some way that makes it difficult to decode it.
Is there a notion of a tensor product? So you could ask self-multiplicativity, for instance, as well.
For natural rank functions.
Yes.
Let's see. Suppose you could ask that. So for example, for geometric rank, subadditivity follows from submultiplicativity, or no, that's subadditivity under direct sums, I guess.
Many things are not, it's like slavery is not something.
It's also a terrible function.
There, yeah, because of that.
It's the reason we added this condition.
But so, I mean, we listed down the minimal conditions we needed to prove the result, right? So I suppose you could ask that for natural rank function, sure.
Does it become easier if, instead of if you're looking for a chord restriction,
Yeah.
right, which has a high rank?
Yeah.
Does it become easier if you allow a basis restriction?
Yeah, that's a good point. So there's results out there that show, I'll call it the core property. Besides, so Thomas proves it for coordinate restrictions, but there's results of Dreisma and Kazhdan and Ziegler that prove results like that for slice rank and Schmidt rank for polynomials in the case of Kazhdan and Ziegler, where they do have to allow for linear transformations to the coordinates before you get, say, a high rank subobject. Yeah, so those results are there, but it's because of this Z that we're working with that coordinate restrictions naturally pop up. Yeah,
Maybe Jan will talk about it on Wednesday. I'm not sure.
maybe.
He will talk.
Right. Yeah.
All right. Thanks.